but I do have walk-ins on Thursday. So if you come to my office 2 p.m. on Thursday, then that's when I have walk-ins. Yeah.
After I signed up for this fall semester, I
Mhm.
just realized my senior year, fall 2026 or fall 2027, I'm not going to have 12 full credits for classes. But then I also recall that you mentioned Kelsey Fullerton is doing that senior elective program that transfers over to.
Yeah. It's a blended BS MS program.
Yes, and so I was wondering if maybe there's an extra class that comes out of that that I can then incorporate into.
So with the blended program, the whole idea is to give you a head start on the masters without adding any additional units. So there would be no additional units that come from that. But so I don't know how the rule would apply because normally our we had kind of a blended program before, and the way it worked was that you would just take extra electives, and then that would count towards your master's degree. But with the blended program, it's all integrated into one.
It replaces those classes.
Exactly. Right? Yeah. But I don't know. I don't know if we're going to allow students to do both the blended program and take extra electives at the same time, or if you have to wait until you're an actual master's student to do that. I think we're still kind of hashing out the rules because it is a new program.
Sure.
But I don't think we've brought that up as a people have brought that up as a potential issue, but I don't think we have a resolution on it just yet.
Okay. If it's worth mentioning, then do you think you could do like a little exemption as a word for, say, veterans who need to have the 12 units but are intending to?
So you can take extra classes, so that's not a problem. But whether it counts towards a master's, then I think we need to discuss that.
Okay.
Another option that you can think about is you can consider picking up a minor. So minor would be a way to kind of. Oh, they're not. I see. So it has to be major courses.
Yeah.
Okay.
And
Let's have a longer discussion on Thursday.
Yeah. Okay.
Yeah.
Otherwise, we'll just sit here like this.
Yeah. Well, yeah, I think that's something that we have to discuss as a department about what we want to do with that.
Is your genius? That's another question.
Sure.
For the plural section, we can take that under any engineering
Yep.
section.
Mhm. Yep, they're all the same.
So the United kids, they're basically registered yesterday. Yeah, the guys, three guys in the class, Diego, Masha, and Diego. Carlos registered this week. What? What? No, they just saw it. I was like, oh, I thought it was possible. Yeah. Thought I Apple will schedule a question. For what? That's not like the senior designs. Well, I'm supposed to think the next one. So get lost. But then, maybe let's like Tuesday. That's pretty easy. I did on they have that there at the school. This year's a little while very slow, like and then I'll get coding.
All right, so 4 o'clock. Let's go and get started. Right, good afternoon, everyone. How's everyone doing today? Good to hear. We are in the final stretch of the semester, so this will be our last topic. Although it's kind of a fairly big topic. We're kind of picking and choosing different ones. But for the last part of the class, we'll be talking about probability and statistics. Now, this is not going to be an expansive treatment by any means, and so you can dedicate an entire semester to probability and statistics and still honestly probably not cover everything. So I'm going to focus just on the ones that are, honestly just important for for your engineering labs. Things like confidence intervals, hypothesis testing, things like that. Okay. So that's kind of the plan for the rest of the semester. There is one more homework just based on this probability and stat stuff. It is kind of a fun, I'd like to think it's a little bit of a more fun homework. So the calculation fund has intense, but you are going to have to do some testing, I will say, right? It depends on how fun you think dropping a pencil from your desk and finding it is going to be, doing that 20 times. So there's that. So we have just 8 more lectures left in the semester, one of which is going to be the exam. So technically just 7 more lectures. And so we're very quickly approaching the end. And so one thing also is that, the topics for today and on Thursday, these are not going to be on the midterm exam. So remember, our second midterm exam is going to be a week from today. So that is Tuesday, April 21st. So the last topic for the midterm exam is going to be Fourier transforms, which is topic for homework 6. So stuff today and Thursday important, but not immediately for the exam. But you can't expect it for the final. Okay.
The reviews can be
yes. So they're my old review video. I don't remember exactly when I've recorded, but it should still be on YouTube as long as YouTube didn't delete it. Which I don't think they have. Okay, all right. Any questions I can answer before we get started? I talked about homework 7, but I haven't posted it yet. I'm going to wait until after the midterm just because I know you probably focus on studying for that. But I'm going to post homework 7 as soon as the midterm kind of drops next week. Okay. Okay. All right. So if there's no questions, let's go ahead and get started. So topic for today is probability and statistics, okay? Or I guess an introduction to probability and statistics. Okay. All right. So first, let's start with the basic statement, right? So let's define a term. Okay. So a term that's going to come up over the next few weeks is what I call deterministic. Okay? And so a deterministic result or deterministic outcome is one that will always happen given a certain set of conditions. Okay. Hence the name. So, for a deterministic outcome, it's something that has already been determined. Okay. And so, I would make the argument that all the math that we've done in this class up until this point, and probably all the math that you've done up for your entire academic careers, with the exception of maybe just you dabbled in some probability and stats, have been deterministic. Okay. So for example, right? So if we have, let's go back to the first midterm, right? So if we have a mass spring damper, okay, where the mass spring damper member is defined by the values of its parameters. So value for the mass, value for the spring constant, and value for the damping coefficient. Okay. So we have m d squared x dt squared plus b dx dt plus kx is equal to maybe some forcing function f of t, right? So we have a second order differential equation where all the parameters and the equation for the system are already kind of determined, okay? Now, if we set values for all of the parameters here, right, and we solve this system, right, what we get is a single function or single value x of t that never really changes, right? So this x of t, you can say, is intrinsically linked together with the set of parameters and the equation that we're solving. Okay. Again, overestimated the amount of space that I had there, but that mass for there is parameters. Okay. Okay, so that is to say that if you have this type of system and you have these parameter values, you're always going to get the same result, right? It's always going to be x of t, right? Okay. So I think deterministic systems are useful for learning math, right? Because you have to learn the different techniques, you have to learn how the different concepts work, right? But I think when I think when a lot of people think of the math that they learn in the classroom and kind of the situations that they experience out in real life, there's always a disconnect, right? So certain phenomenon that you experience in real life are very rarely deterministic. Okay? So there's always some degree of uncertainty with the result, right? So it's very hard to make predictions of exactly something that can happen because you can't always account for everything. Right? So uncertainty is kind of the concept that we're going to start to really account for, and it's one that's going to come up a lot as well, right? Because there's just certain things that happen in real life that you just can't predict for, and that's going to create uncertainty in your result. Okay, now let's do an example really quick. So I think the easiest example that you can think of for this is if you think about your commute to school or your commute to work. Okay. So if you ever ask anyone, how long it takes them to get to school or how long it ever takes them to get to work, right? No one ever gives you an exact answer, and and it's not something that you can give an exact answer for, right? So if someone asks you this, usually you say, maybe about like 45 minutes, right? Right. You can never say with certainty, whether you're going to arrive at a particular time or how long it's going to take, right? Even if all of the variables that you can control are exactly the same from day to day. So let's say you leave at the exact same time, right? There's no guarantee that you're going to arrive on campus at the same time. Okay. So some examples of things that can happen, during your commute, just very simple traffic lights, right? So you can't control just how the traffic lights are. Maybe some days you get all green lights and you just shoot down the street and arrive very quickly. Or some days you just catch all the red lights. But then, the reality is sometimes you catch some combination of green and red lights, right? Traffic, right? So you can't really control how many cars are going to be on the road on a given day, and that's going to affect your commute as well. Okay. Right. So very few real life events, as hard as we try to predict things, as hard as we try to mathematically model things, there's just some aspects and some things that we just cannot predict, right? Which is a very, I would say maybe disconcerting thing to say in a class like this, where this class is all about mathematical modeling and being able to make those predictions. It's interesting. I think about these, so probability statistics is not something I really learned a lot until I got into grad school, honestly. This was not something that was part of my undergrad curriculum, but ever since I learned it, it's something that I think about almost on a daily basis. So one thing about myself, I'm a big sports fan, so I like to watch sports a lot. And if you ever follow kind of a sports game online, you'll see that they've added something recently called the win probability tracker. So, depending on the score of the game, the conditions of the game, there's the tracker that tells you, what percent chance the team is going to win. And it's never 100%. So even if you're up, say, like 28-3 in the Super Bowl, you're not 100% guaranteed to win at that point. As just after the Atlanta Falcons, so they know very well what happened there. It's only after the game is over that tracker actually goes up to 100%. So anything can happen, and you never know what can happen with uncertainty, right? And so in the face of such uncertainty, you may think that, maybe everything that we learned in this class is useless because if there's so much uncertainty in the world, there's really no point in doing mathematical modeling, right? But, I'm going to make the argument that, uncertainty, while you can't avoid uncertainty, it is something that you can actually model as well. It's something that you can actually work with and factor into your mathematical models, factor into your engineering measurements, and still get results that are ultimately very useful. Okay. So the whole point of this section that, and for the rest of the semester is not to say that, uncertainty makes everything really difficult and impossible to model, but, there are ways that we can work with it and still get useful results. Otherwise, we wouldn't be able to do engineering.
Is it like figuring out which mathematical model will produce the least amount of standard deviation?
That's part of it. Yep. So that's part of it. But also just part of it is just understanding just how much uncertainty is in your model. And so by the time maybe you do mathematical modeling, you not only get your result, but you get some error bars in your result. Say that, this result is reliable within this particular range. Yep. So that's one of the first things we're going to learn, which is confidence intervals. Yeah. So that's kind of the broad motivation of the last 4 weeks of class that we're going to do. So we are going to build up these topics kind of little bit by little bit. So today we're starting with kind of the absolute basics, and so I think probably a lot of what we're going to learn today you've seen before. So concepts like mean, median, and mode, data representation, box and whisker plots, histograms, things like that. So today I think we're going to just start with the basics, and then we're going to build up kind of more advanced concepts from there. Okay. All right, any questions on anything that we've discussed so far? Okay, all right, so let's start with something very simple. So let's talk about how do we represent data. Okay. So when I talk about data, usually data is in the form of some kind of measurements of some observed phenomenon. Okay. So those measurements can be something as sophisticated as, maybe like an engineering type of measurement. So let's say you're doing, some kind of, testing in an engineering lab, and just whatever you observe, the measurements you get from that, you can represent that in a data table, or it could just be something mundane. So, maybe you track and you write down how long it takes you to commute to school every day, for the next, for the last 4 weeks of the semester. And then you track that with data as well. So data can refer to any of these. And so it doesn't necessarily have to be an engineering type of analysis. Okay? So the simplest way to represent data, because usually with data, you have some kind of numerical value associated with the conditions that were present to produce that numerical value. You can just have that listed in a table. So for instance, let's say that we did, keep track of, every day for an entire semester, how long it takes us to commute to school. Okay. So this is not the only format for the table. And so, there's lots of different ways to format a data table like this. But the most important thing is that you write down basically every numerical measurement that you obtain. Okay. So let's say that, for a given semester, let's say that we make rows for each of the weeks of the semester. So week 1, 2, 3, 4, and let's say that we track our commute times for each day of the week. Right, so we have just a simple data table that looks like this. Okay. All right, so let's say on Monday it took us, maybe 42.37 minutes. Tuesday, maybe it took, 47.44 minutes. Wednesday, let's say it took us, 51.45 minutes. Thursday, maybe we go fast that day, maybe 38.10 minutes. Friday, let's say that it's a good day, 35 minutes. Okay. Right, and then so on and so forth. So the idea is to just kind of give you a nice, easy format to write down your measurements. So a table, I guess technically a table you wouldn't classify as data representation. I would say this is more kind of data recording. But usually when you're first running your experiment and you're first collecting measurements, a data table is usually what you're going to be using first. Right. So it's probably a concept you're all familiar with because you've all taken lab courses and you've taken measurements and they're always going to be put in the table. Okay. Okay. All right, so while tables are very convenient for recording, it's very easy to just kind of see just kind of what's there. Um, it's very difficult to pick out trends or visualize trends or patterns in the data. And a lot of times, when you are taking measurements of some kind of phenomenon, that's something that you want to notice, right? So you want to see what the trend is. Maybe it goes faster on maybe your commute time will go faster on Mondays because maybe they don't do construction on Mondays. Maybe they go faster on Fridays because a lot of people work from home on Fridays, right? And so you want to be able to kind of see those kinds of patterns, or maybe you want to see the correlation between maybe how long it takes you to get to work versus what time that you leave, right? So there's lots of different associations that you can do. And you might be able to pick up, small things here and there just by looking at numerical data, but it's you're going to miss out on a lot of stuff because it's oftentimes there's a lot of data to kind of process just by looking at a table. Okay. And so with that, the next step after you take a just a numerical recording of the data in a table is to graph the data in some way. And so, again, we're not going to go over an exhaustive list of all different graphical ways to represent data. But, we'll go over some important ones, at least to kind of fuel our next discussion over the next couple of weeks. Okay. Okay. So the first type of way to represent data is we're going to go over a histogram. So a histogram is very useful because it's graphically a very easy way to show you which entries or which values in your data show up most frequently relative to the other entries in your data set. So the way histogram works, is kind of like the following. And you can customize, how your histogram looks as well. But generally for a histogram, you're going to sort your data into various different bins. Okay? And so how large or how small the bins are, that's something that you typically can control. Okay. But you usually want the bins to be big enough, right? Just so that you don't have a lot of empty bins, but you don't want them to be so big that you don't see any trends in the data. Okay. All right. So for example, a sports example, but one that hopefully is pretty not too hard to understand. And so let's say we make a histogram of the heights of all the players in the NBA. Right. So, typically to play basketball professionally, you have to be pretty tall. And so, you're going to see here that the histogram is going to trend more towards the right. Okay. So for instance, this is kind of what the histogram would look like. Right. So I'm sure you guys have seen histograms before, but maybe not to this detail, right? So on the horizontal axis, that will be the values of your data. Okay. So in this case, since we are comparing heights, right, the horizontal axis will show the different heights. Right. And then let's say that we're going to display the height in inches. Okay. And so let's say that we have, we start at 65 inches, 70 inches, 75 inches, 80 inches, 85, and 90 inches. Okay. Okay. And so generally, you're going to see, for NBA players that are typically very tall, our histogram is going to be skewed more towards the right. Okay. So for instance, you might see blocks like this, where the heights of these blocks will kind of tell you, approximately how many of those players are that height in the NBA. Right. And then once you get to the really tall players, this is where things kind of, peter out. Right. And on the other end, you may have some outliers that are, very short as well. Okay. Right. And so, of course, with any data set, with any kind of large amount of data, you're always going to have some kind of outliers. And so any histogram entry that is kind of very small in height, these are what we call outliers. Okay. Just because they don't fit into the general trend, they don't fit into the larger bins, but they are present in the data. Okay. But in general, you can see here that most NBA players are going to be around that height, maybe 80, 85 inches around there. Okay. Okay, so histogram, very, very simple way. It's you can almost think of it as kind of like a graphical way to display the mode of your data set, right? And so if you want to, which value is going to show up most often, then this is a great way to. Right. I want to emphasize the histogram because this is going to lead into another topic that maybe we won't cover today, but definitely by Thursday, which is the probability distribution function. All right, but we'll cross that bridge once we get there. Okay. Any questions on histograms? Okay, so another popular way to graphically represent data is through what's called a box and whisker plot. Okay, so the whole idea with the box and whisker plot is to show you, first of all, it's a box and whisker plot is a nice way to show the median of your data set, okay, as well as the different quartiles in your data set as well. Okay. So quartiles is a concept. So you may have heard of the concept percentiles before. So quartiles is kind of the same idea. So the quartiles will tell you, kind of the different thresholds within the data. Okay. And just like the name implies, quartile splits your data set into 4 different kind of bins. So the first quartile, the second quartile, the third one, and the fourth, based on their ranked values relative to each other. Okay. Okay. So for example, my little bit, little personal story again. My son was born back in July, but he was actually born premature by about 10 weeks. So he is very small for his age. And so every time we go to the doctors, they weigh him and they said the doctor's like, your baby's in the second percentile of weight. And so that basically means that 98% of babies that of his age are way more than him. And his height, so his height's not doing any favors. So both my wife and I are very short. So even if he was born normally, he would still be in probably the second or third percentile. But his height is only the first percentile. That means 99% of other babies are, taller or longer than my parents. So box and whisker plot kind of has this same idea, but with quartiles instead of percentiles. Okay? So for instance, okay? So box and whisker plot, maybe look something like this. So if we take the same data set, so let's say we took the data set of player heights in the NBA, and so, but now we're putting that data on the vertical axis here. So the first thing that you put in a box and whisker plot is the box. So the box is going to represent basically the middle quartiles of your data set. Okay. Right, so let's say we put a box just like this. Okay. Okay. And so the idea with this box here is that 50% of your data set is going to have values within this box. Okay. Right. So that means the lower end of the box. Right. This right here is the cutoff for the first quartile. Or I think, if percentiles are a little bit easier to understand, this is the 25th percentile. Okay. And then the upper end of the box, this is going to be the cutoff for the third quartile. Or in terms of percentiles, this will be the 75th percentile. So in other words, all the data that's within the box are going to be between the 25th and the 75th percentile, or in other words, 50% of the data set. Okay? And another thing that you'll see inside the box, there is always going to be a red line. Now, sometimes the red line is completely in the middle, but sometimes it's not. Sometimes it might be shifted. And so that red line there will tell you the median value of your data set. Okay. So the concept of a median is actually very interesting because, median and mean, I think people kind of equate them to be the same. So it's, a lot of times they are the same for a data set. But sometimes you might have medians and means that are actually far off from each other. Right? So that line there, so when you see box and whisker plots, so let's say you're reading kind of a research paper, box and whisker plots are very popular in research papers. You'll see that line for the median might be shifted more towards the 75th percentile, or it might be shifted down towards the 25th percentile, depending on the nature of the case. Okay, so that's the box, right? So the box is kind of is there to kind of show you the absolute kind of average, the average of the data set, right? That's the whole point of the box. But then we also have the whiskers. And so the whiskers are lines that kind of extend up and down from the box. Now, given this data set, I think those lines are a little bit long, but I wanted to kind of make them long to exaggerate. Okay, so the whiskers here, okay, the whiskers show you the absolute limits of the data set. Okay. Okay. So the whiskers are there to kind of show you the absolute breadth of your data set. So the absolute max and the absolute. Okay. So for NBA players, I think there's no question about who the tallest player in the NBA right now. This is Victor Wembanyama, right? So he's a French dude. He's like 8 foot tall or something. He looks gigantic. And then the shortest player, I'm actually not sure. I know there's a Japanese guy who plays for I think he plays for Memphis right now. So he's pretty short. He looks like a traffic cone out there playing against real NBA players. Okay, but that's box and whisker plot. So I did want to bring that up because once you kind of get further along in your engineering career, and especially if you're doing research, you'll be reading a lot of papers, and box and whisker plots are very popular for research. And this actually wasn't properly explained to me until I was in graduate school. So it's good to know exactly kind of what the box and what the whiskers actually mean for these plots. Okay. Okay. All right. Any questions on this? Okay, good. Okay, so of course there are other ways to represent data. Another very popular one that we'll go over, it'll probably make more sense later on, is a scatter plot. So that's probably the one that I personally use the most often just in my own work, but I think we'll save that discussion for when it's a bit more appropriate. But when you're talking about just like a data set with that has certain values, histogram, box whisker plot, I think are just kind of the basics of what you should. Okay, so let's get into more numerical values then. So let's go over just concepts of mean, median, and mode. Okay. So, these three concepts of mean, median, mode are often discussed together. This is something that also that's taught very early, often for students, right? And so they all basically represent different things about your data. But I think, the reason why these three concepts are discussed together is that, there are different ways to kind of show you or to illustrate what a typical member of your data set would look like. Right, and I put typical there in quotes because, typical can mean different things because, mean, mean, and mode, they all have different definitions. But the idea is that if you were to just look at your data set at a glance, right, and you were to pull out maybe just say a random member from the data set, the mean, median, and mode will tell you, what you should expect from that. Okay, so let's just go in order. So let's talk about the mean first. Okay. So the mean, as you probably know, the mean is simply just the arithmetic average of all the values of the data set. Okay, so typically for mean, the way that we describe it is with the line kind of over the top of the variable. Okay. So let's say that X right there, X is a member of our data set. So we'd say the mean of the data set is just X with the little kind of flat line on top. Okay. All right. So the formula for arithmetic mean, you don't really need a formula for this. I think everyone's computed means at some point, but it's just going to be 1 divided by n, where n here is the number of entries in the data set. Okay. Multiplied by the summation of every entry in the data set. So we have summation of I up to capital N of xi. So that's just a fancy way to say, you just add up all the entries in the data set and you divide by the number of entries, okay? And that gives you the mean. Okay, very simple. Next, let's go over median. So the concept of median actually it kind of refers back to our, box and whisker plots. Okay. So the median is the basically 50th percentile value. So if you were to take all the entries in your data set and just, list them from the least to the most, the median is the one that's right in the middle of that list. Okay. So the median is literally if you took all the data and all the entries in your data set and list them from least to greatest or greatest to least, doesn't really matter. You pick the whatever is right in the middle, right? So that value tells you that 50% of the entries in the data set will have a value that's greater than this, and 50% will have a value that's less than this. Okay. So perfectly right in the middle. Right. And then finally the mode. Second. No, the mode is the entry that that appears the most often. Okay. So once again, I think the easiest way to find the mode is to list is just to sort your data from least to greatest and greatest to least. Find the entry that appears kind of most often, and that will be your mode. Okay. Now for certain data sets, it'll be hard to identify a mode just because it's so let's say that you're measuring the time it takes you to commute to school, right? More than likely, you're going to have no two times are going to be exactly the same, down to the second, right? And so oftentimes the mode, the best way to do that is to first of all make a histogram of your data, and then whichever column in your histogram is the highest, that's going to be your mode. Right? Most of the time, mode is not terribly useful for most, I would say, practical data sets. It's more just kind of trivia in terms of your data set. Most time you're using mean and median to say anything substantial about your data set. But mode is, if we're talking about mean and median, we might as well just mention this one. Okay. Okay. Now for a for I would say a nicely behaved data set, we'll define a term later called Gaussian. And so for a typical Gaussian data set, these three indicators or these three metrics, they're going to be roughly the same. So the mean would be right where the middlemost value is, which is always going to be the value with the highest column in your histogram is going to be. Okay? But what's interesting about probability in stats is that most data sets are not going to have that very nice distribution. And so you're going to have some things that skew the data. Okay. All right. So let's go over a very quick example to kind of illustrate this. So there are certain data sets or certain types of data where the mean, median, and mode can tell you very different answers. And so, for example, let's consider, let's just look at California. So let's consider, if you took all the households in California and you listed out their, yearly income, right? And then we computed, let's say, the mean, median, and mode of that data. So I'll preface this where I first wrote these notes in 2019. So this data is from 2019. Okay. So in 2019, the median household income in California was $63,787. Okay. While the mean, right? So just the simple arithmetic average of all the household incomes in California was much higher. It was 91,140. Right. So you can see these values are very, very different from each other. And I haven't looked at the data for 2026, but I would imagine that discrepancy is still there because the underlying causes for that discrepancy are still present. They might be even worse. Okay. So what's going on here? So what could possibly lead to certain data sets like this, where you have a mean and median, which they're both the mean and the median are there to represent what a typical member of your data set is, right? How can you have such different different pictures of what a typical member of this data set could look like? right? So the answer to that question for this particular data set, obviously, is a very complex question, but to kind of say it very plainly, right? In California, we have a lot of, I would say, very high income earners. So there's a lot of a lot of people that work in tech up in Silicon Valley. We have a lot of people that work in the entertainment industry in Hollywood, right? So these people have very high household incomes. And so if you think about how these two metrics are computed, right? So for the mean, right? To compute the mean, you actually have to add up all of the values for everyone, right? No matter if the value is a very gross outlier or if someone is a very kind of typical, right? And so the mean, what people say is the mean is much more sensitive to outliers in the data. Okay. So because in order to compute the mean, we do have to actually sum up those values. That means any kind of outliers in the data on both ends of the spectrum, they're going to skew the data, which in this case is going to skew the data towards the right. Okay. Whereas the median, if you think about the median actually doesn't really care too much what the values are. The median just requires a ranked list, right? So a lot of times people say that if you want to look at kind of what the average kind of person in California is experiencing, don't look at the mean because the mean is going to be skewed by a lot of outliers that we have in the state, right? The median is much more representative of what people are because for the median, we're not necessarily adding people's values together. But we are just looking at just a ranked list. Okay. So I'd say, for this particular data set, I would argue that the median is probably a better representation of what you would consider kind of be what an average Californian family is experiencing. So does that mean median is always going to be the better metric for certain data sets? No. And so there are some data sets where the mean is actually going to be more important. It really kind of just depends on the nature of the data and kind of what is being measured and what kinds of conclusions are being drawn. Okay. And so, next time that, and statistics are kind of abused a lot in kind of the news and social media and everything like that. So, pay attention to kind of what they're saying because, people do actually make the distinction and they say that, the median is this or the mean is this, right? So kind of pay attention to kind of what people are saying about that and kind of think about, what that actually means for this particular data set. Because, the mean and the median and mean, you can see for this case can kind of tell very, very different stories. Okay. Okay. All right. Any questions on this? Okay, good. All right. So that's mean, median, and mode are great ways to kind of represent your data, and they all kind of show something a little bit different. And so kind of knowing what they represent is always good. Okay. Okay, so now that we've kind of seen what a typical member looks like, let's talk about kind of variances within the data. Okay. So next concept is going to be variance and standard deviation. Okay. All right. So in addition to mean, median, and mode, right, it's often useful to say, how much variance or, how much a member varies from another one in a typical data set. hence the term variance and standard deviation, right? So for example, let's consider two very simple data sets. These two data sets are going to have the exact same mean and the exact same median, but you're going to see that the data sets themselves are very, very different from each other. Okay. So let's say we have data set A, and so data set A will have 5 entries. It will be -2, -1, 0, 1, 2. Okay, so I've already ordered them in the right order for you. And data set B will be -200, -100, 0, 100, 200. Okay. All right, so if you computed the mean and median for both of these data sets, they are exactly the same. So both have a mean of 0 and both have a median of 0 as well. Okay, but I think you would give pause to say that, if someone were to say that, oh, these two data sets have the same mean and median, so they must be very similar data sets, right? Well, they're not. They're very different. So is there another metric that we can use to say that, data set B, if you look member to member, there's much, much more differences between there, right? So, from one member to the next, there's at least a difference of 100. Whereas for data set A, there's only a difference of 1 between the data sets, okay? So there is a metric for that, which is called the variance. And there is a formula for variance, although it is not it's not a straightforward looking formula. This is I think people always remember the formula for mean. Variance is one that people kind of conveniently forget because it is a little bit harder to use. Okay, so the variance of a data set, usually we give it the symbol sigma squared. And the reason we square it is you'll find out in a second. Okay. But the formula for that is 1 divided by n minus 1. Okay. Where n has the same definition as before. N is just the number of entries in your data set. Okay. The -1 is important. You do need the -1. And you multiply by summation from I is equal to 1 up to n. Okay. And then what you're summing up is going to be the difference. And so you're going to take the difference in between a particular data entry I minus the mean. All right, so to compute variance, you do need the mean. Okay. All right, so basically we're going to take the summation of, we're taking the difference between each individual data entry minus the mean. So the more varied your data is, right, that difference between the entries and the mean is going to be larger, okay? And then just to make things positive, right, just because, you can have variances above and below the mean, we square it, right? So that's all the square kind of really does. Because if you have some positive, some negative, then they're going to cancel out, and that kind of, it doesn't really show you the variance at that point. So it just, you're going to get something that's misleading. So we square just to make sure that all our differences are constant. Okay, so that's the formula for the variance. Okay. So the reason we have -1s, the reason we have 1 over n minus 1 in front is the fact that, for the variance, we're taking essentially differences between two entries in our data set. So, and so we have the n minus 1 there just to say that, we're not summing up over all the different entries, but we're summing up all the different differences in the data set, if that kind of makes sense. And so to make a difference, you need at least 2 entries. And so, that's why we have 1 over n minus 1 now. That detail is not too important, but, if you were ever curious kind of why there's a 1 over n minus 1 in front of the variance, that's the reason. Okay. So if you compute the variances of our two data sets, right, obviously data set B is going to have a much higher variance than data set A. right? Just because from entry to entry, we have a difference of at least 100. Okay. Okay. All right, so that's the variance. I would say in terms of interpretability, variance is a little bit harder to interpret just because it's we square, right? And so if in terms of units, right, variance will always have the same units as our mean squared. Okay? And so, for instance, if you were to take the variance of the player heights in the NBA, right, whatever we compute for the variance, the units for that will be inches squared. Okay. Which makes it a little bit hard to kind of say, because oftentimes, we want to look at the variance and we want to say that, the average kind of deviation between data entries is this. But that's not what you're getting with the variance. For the variance, you're getting the average difference squared. Okay. So with that in mind, we mathematicians invented another term to make that to kind of fill that gap of interpretability, which is called the standard deviation. Okay, so the standard deviation, very simple to interpret. Standard deviation is just the square root of the variance. And the reason we take the square root is just so that it will have the same units as our mean. All right, so standard deviation, usually we just give it the simple sigma just by itself is equal to square root of sigma squared. With a sigma squared, remember this is our variance. Okay, so very straightforward. So the standard deviation is much more easy to interpret because it does have the same values as the mean. Okay, so what you'll see typically done, right? Kind of a very naive, kind of a very kind of simple way to display kind of uncertainty in a measurement is to display the mean plus or minus the standard deviation. All right, so let's say that we have a mean plus or minus standard deviation. And probably, first time you learn about standard deviation, this is probably how you use it. As you said that, whatever measurement you've got is going to be mean plus or minus the standard deviation. Okay. And so what that's telling you is that, what you can expect is that, you are basically conceding that, you are dealing with an uncertain quantity. But if you were to take your uncertain quantity and measure it multiple times, right, you're likely to get values that are within this range right here. So you have to be careful with standard deviation too. I think when some people see data that's like this, right? They think that the standard deviation may represent the absolute max and the absolute min. So, the standard deviation may be that, people think it's like the average plus the absolute max minus the absolute min, right? But that's not what it shows. So the standard deviation doesn't show you the absolute limits of your data set. It just shows you kind of what a typical range would be, okay? But, there's a reason I call this a very naive way, right? Because this interpretation and this kind of displaying of the data does assume that your data has a certain character, has a certain trend. And what that trend is that we're basically making the assumption that our data is Gaussian. Okay. So there's that term again. So, I brought up the term Gaussian before. Okay. And so if you've seen a Gaussian distribution, or you've probably seen a Gaussian distribution, you just didn't know it was called a Gaussian. And so kind of another, I would say the more popular term for Gaussian is a typical bell curve. Right. So Gaussian distribution looks like this. Right. So let's say that we have an upside down bell, or I guess an up forward facing bell, just like that. Okay. Where the mean is just whatever values in the middle. And there's kind of a symmetric peak that kind of, goes down on both sides. So, you have basically equal variations to the left and right of the mean. Okay. Okay, so if you're going to display your data as mean plus or minus standard deviation, you're making the assumption that your variable or your measurements are Gaussian in nature, okay? Which a lot of things are. And so, there's a reason that, Gaussians are used, because, I would say a lot of things do kind of fit that distribution, but not everything is going to fit the Gaussian distribution. Okay. Okay. And so, of course, that is a good segue for us to talk about probability distribution. So I think for the last 10 minutes of class today, we'll kind of introduce the concept of a random variable and probability distribution, but we'll get more into it on Thursday. But before we jump into that, are there any questions just on variance or standard deviation? Okay. All right. So let's talk about random variables and probability distributions. That'll be the last thing that we talk about for today. Okay. So when we started class today, we introduced this idea of uncertainty, and that affecting the value of a deterministic variable, right? And so we kind of basically started by saying that most things that you observe in the physical world, there's going to be some uncertainty to it. Okay. Another way of kind of saying that very simple fact is that every time that you make an observation of a phenomenon that's subject to uncertainty, the value that you observe is going to change quickly. Okay. And so if you kind of look at it from a slightly different perspective, right, we can say that any kind of random event or any kind of random variable, which is subject to change every time you observe it, we can call that a random variable. So random variable is one where its value will change. Okay. Or maybe that's not the way to say it. This random variable is one where every time you observe it, you will get a different result. So, by introducing random variables here, we're making a subtle shift, right? So up until this point in the class, we've been talking about just data sets. And so data sets represent data that has already been observed. And you're just kind of, computing different metrics and analyzing that data. When we're talking about random variables, we're also talking about kind of random events. Or in other words, we're making predictions in terms of what can happen, to something that is subject to uncertainty, but may not happen just yet. Okay. So for example, okay, so we can use a random variable to represent your commute time. Okay. Right. So you have, you can record data on your commute time, right? But if you want to ask the question of, what is going to be your commute time tomorrow, right? We don't know because we haven't observed that yet. But when we do observe it, right? So when you do actually go through your commute, that that amount is subject to uncertainty. So therefore, your commute time is a random variable. Okay. Okay. So even though random variables are random, right? They're not completely random. Okay. So I use the word randomness here just to kind of just to kind of communicate the fact that these variables are going to change every time you observe them, but they're not random in, I think, maybe the colloquial sense of the word, where it just takes just any value impossible, right? So there are limits to a random variable, and of course it depends on what the random variable is representing. But there are kind of limitations to the particular values that it can take. And so what we can say is that for any given random variable, there is always going to be a range of possible values where the random variable can't take values that are above or below the range. Also, we can say that the random variable will have certain values which it prefers. So that is to say, certain values, if you were to observe your random variable repeatedly, there are certain values or certain ranges of values that are going to show up more commonly than others. So those are going to be the values that it's, that it prefers. Okay. All right, so how do we represent this information, right? And so it's when you talk about all the different possibilities of different random variables and all the different ranges and all the different preferred values, right? That kind of begs the question, is there kind of a very kind of compact, very succinct way to kind of describe a random variable? There is, but it's usually a graphical representation, which is the probability distribution. Okay. So that graph that I just showed maybe 5 minutes ago of a Gaussian random variable, right? So that graph is what I would describe as the probability density function for a Gaussian, okay? By the way, you'll see me use this acronym a lot. So I'll say RV. RV stands for random variable. Okay. So Gaussian, I think, is kind of the easiest random variable to kind of understand, or one of the easiest, I would say. Okay. So for a Gaussian, right? If you think of a Gaussian curve as similar to a histogram, right? You'll see that there's one clear peak. Okay. And so the peak there will kind of show you what the preferred value of this random variable will be, right? So even though there's some spread in the data, most of the time when you sample the random variable or observe the random variable, it's going to be around that peak. Okay. Whereas the tails of the Gaussian, that will show you kind of the range of possible values that can occur. Okay. Okay. So probability and stats, so we'll stop here for today just because we're out of time. So probability and stats I think it's fascinating. I think it's really interesting. And the rabbit hole was very, very deep. I remember, so one of my professors in grad school, he would always say that life is a POMVP. And POMVP is an acronym for partially observable Markov decision process, which is a concept way beyond this class. So we're not going to go over it. But there are, lots of things with stats that we can. I told my wife that too. So in my wedding vows, I said that, life is a POMVP, which stands for partially observable Markov decision process. And she gave this like really kind of disgusted look, and the photographer caught it, which is perfect. I love that. My favorite picture from our wedding. Okay, so thank you guys for coming today. I hope you guys enjoyed the class today, and I will see you guys on Thursday.
There's one that Thursday is probably the last chance I have to get with you on the exam.
Okay.
And discussing some of the questions.
Yeah.
Can I still schedule an appointment with you, however, in the future?
Yeah, of course. Yeah. So I mean, the next couple of weeks are be busy with advising just because we have this registration. But usually by the end of the then my schedule kind of will that. So, but Thursday I have office hours for the class from 1 to 2.
1 to 2.
Yeah. And then my advising hours from 2 to 3. And so if you just want to stick around, you can talk about the class from 1 to 2, and then maybe do advising from 2 to 3.
Yeah. Nice.
Yeah.